smelter operations. So copper converting in general is a step where a lot of extra heat is produced, and that means that converting step can utilize a lot of scrap which doesn't have any heat value, so it acts as coolant there to kill the extra heat. Now, in this situation where we are now, a lot of electronic scrap and multi-metal kind of end of use things are coming to collection and recycling steps. So this will change converting a bit, and also the products of converting step, and probably also some processes within smelting and converting, like flue dust treatment, in order to ensure that all metals are recovered in an efficient way. So metal converting is mostly today carried out in converters which are horizontal cylinders called Pearce-Smith converter. It is rather old equipment, more than 100 years ago invented, and it is probably producing 90% of all crude copper we are making today. So it has a lining of refractory bricks. It is tiltable. These wheels are allowing its movement along its axis, and the whole converting furnace is also equipped with hoods which are capturing as much as possible of the SO2 and allowing charging and of matte and skimming slag from the converter through this mouth. So converter doesn't have any kind of heat source, no burners, no heating devices at all. It generates all the heat necessary for melting fluxes and learned during Imam's from lecture. So this is the phase diagram, binary phase diagram, without an endpoint of copper converting. First step. So first step is we call it white metal. Binary copper. Isobars, so is iso partial pressure curves with curves with the same partial pressure. So from here From here, you can see it is going down from 100 atmospheres. That these are logarithms of sulfur pressure, down to 10 to minus 2 atmospheres. And here is something which was wondering you in Imam's lecture. This is a miscibility cap where we have two molten phases in equilibrium with each other. This is the sulfide matte phase, the white metal phase, and here in equilibrium, on this phase boundary, we have molten copper containing small amounts of sulfur. So this makes the process possible. We are reducing in converting. We are first reducing iron content of the furnace mat. That is called slag glow. And once all iron has been depleted, has been oxidized away, we start the second phase or second step of converting process, Beer-Smith converting process, called copper glow, when we are coming along this tie line from copper matte to metallic copper along this isotherm, so constant temperature line, which is, as Imam told you, it is called tie line. It is connection between two phases in equilibrium with each other. And once all sulfur has been oxidized, we are here at certain temperature, which we are using in converting. It's not 1400, it's between 12 and 1300 in industrial operations. But anyway, the process goes exactly like that, and you can see it from the phase diagram how the matte is behaving from this diagram after the iron has been oxidized away. And then when we continue the oxidation, sulfur content is decreasing in molten copper. And what we have, as you will see, we have crude copper containing sulfur and oxygen. I will tell you later why we have oxygen in there. So this is an enabling scientific background why copper converting from molten copper matte is possible. And really it is done in two steps. First, slag glow, where we are oxidizing iron and forming slag. And then in the second step, we are oxidizing only sulfur and not actually generating slag, but only gaseous sulfur dioxide. So the reactions are here. And in normal cases, in current copper industry in the world, they are producing furnace matte from flash melting or other smelting furnace, which contains from 60 to 70% copper. That means that there is about 15% iron in 16 matte grade and about 5% iron in 70% matte grade. And this iron, independently where we start from, this iron will be removed in the first step of converting, and that first step generates both, as we see here. It generates SO2, gaseous sulfur dioxide, and then it generates from iron oxides, ferrous oxide and ferric oxide, which is often precipitating in the converting stage as magnetite from the bath, from the slag bath. Often Peer-Smith converters are magnetite saturated when they are doing the job. And typical sulfur concentrations where we start from are between 21, probably in case of 70% matte grade, to 23 weight percent sulfur in the low end, low copper grade end of the furnace matte. So all these extras will be removed during Peer-Smith converting step 1 and step 2. And that step 2, when we don't have any more iron there, so it is generating again with oxygen. It is generating gaseous SO2, and there's no slag forming reactions taking place anymore. So once we have done that, once we have removed all sulfur from extra sulfur from our copper matte and reached this phase boundary, so we start producing, along with loss of sulfur, we start producing copper, molten liquid copper, which is then separating from the matte. It's more heavy and it doesn't dissolve chemically into this sulfide. So it forms droplets, and in the end it is collected in the bottom of the converter and forming a layer of molten crude copper. So this is how it goes, and in general we have our copper making chain from smelting, then we come to converting, and after converter we treat still this crude copper generated in the Peer-Smith furnace. We treat it in an anode furnace for making suitable material for casting anodes. What kind of slags we are using in the converting step? Now we don't have any more these gangue minerals which are in the concentrates. So we are having only those materials in the converter charge, which dissolve in the furnace matte. So we have typically, along with copper and iron and sulfur, we may have nickel, we have precious metals, we have platinum group metals, we may have cobalt, antimony, bismuth, and such trace elements, but no no MgO, no alumina from the gangue, no extra silica from the gangue. They all are dissolved already in the smelting furnace, in the smelter slag, and removed from the raw material feed of the converting step. So that is why it is very straightforward and a simple solution to use the same flux for iron oxides as we use in the smelting step. So silica, and now the forming converter slags are relatively pure iron silicate slags generated from this ternary system of ferrous oxide, ferric oxide, and silica. So this is now more simple slag. We can predict very easily how it behaves as a function of composition, as a function of oxygen pressure, and as a function of which I could call fluxing rate or fluxing degree, how much silica we are adding in the converter. And often in converting step, we are using phase diagrams like this. This is a special type of projection of the normal phase diagram Imam showed you and I showed you on Monday on iron silicate slags, but it is a composite of several isotherms as a function of the mass fraction of iron, and then there is this ordinate axis is the prevailing oxygen partial pressure of the system. So we are moving in converting from the low or lower oxygen partial pressure of the furnace mat to higher oxygen partial pressures of the crude copper. The unit here is Pascal. It's not atmosphere, and that is why these numbers may look odd, but they typically 1 Pascal is about 10 to minus 5 atmospheres. So this is this top here, which is at 1275 degrees C. So it shows that homogeneous slag domain at that temperature is within these lines, and it is composed of several concentrations of iron in iron silicate. We often examine these slags using weight ratio of iron to silica in the slag. So this iron silica ratio runs from 1 to 5 in this diagram. So it's total iron divided by total silica of the system. And in here we are at low iron silica ratios. We are saturated, our slags are saturated by silica, and at high iron silica ratios they are saturated with spinel or magnetite, as the common word is said. So these kind of diagrams can easily explain to you how converting is carried out, and it's in which areas of the slag system you are. Are you in silica saturation? Are you in magnetite saturation? Are you in homogeneous slags? Are you in heterogeneous slags? Why the viscosity is low at some point, and why it is high in some compositions or oxygen potentials, oxygen partial pressures. So in this sense, copper converting slags are a simplified version of copper smelting, and this is why the issue of slags is not as important in the converting step as it is in the smelting step. But what is important is that because you are adding cold sand into converter, so there may be difficulties in the first minutes or tens of minutes of copper blow and slag blow to maintain correct temperature for the slag. So slag formation, how it is carried out, it's not thermodynamics, it's not actually of any other scientific issue. It is more or less practicality, how the operation is carried out at the smelter, how the stable temperature is achieved as early as possible, and how it is maintained so that the charge does not overheat, how cold coolants are added, and in which way silica sand is added into converting when the converting is going on, when more and more iron is transferred from matte to the slag as oxide. So this is very important in terms of losses. When we are doing batch-wise operation, we are skimming, we are taking away slag. The amount, concentration of copper is important in the slag which is taken out. So this is how this is dependent on how the operation is done in the converting step, in Pierre-Schmidt converting step. In general, in all metal making at high temperatures, but I take it now here because I have somewhat more time here than yesterday or earlier. So we have two types of metal losses in the slag. We have chemically dissolved metal in the slag, which is a result of oxidation reaction like this. So copper in matte or metal reacts with oxygen and ends up in the slag as oxide. This is called chemical dissolution, and this is what we can adjust by selecting endpoints and operation conditions, how oxygen is blown and how much time is given to settling and separation of phases, and how long the oxidation is carried out in each step. So this is about the skill of operator and the plant. What is the local practice in operating a furnace, in this case Pierre-Schmidt converter. The other form, which is often much more in terms of copper concentration in copper making, is the mechanically entrained copper or copper matte. which can be due to unsettled droplets, fine droplets of metal or matte, which don't have, for certain reasons, they don't have time to settle, or they are due to kind of too hasty operation of slag tapping. This is an experimental study from about 20 years ago, which was carried out in Australia by one of my colleagues from Finland. He was studying the entrainment of phase due to velocity differences in tapping. So here we have, this is a water model, and these arrows are measured velocity velocities in the liquid, and this is the lower, more heavy liquid in here, which is moving very slowly, and this is typically matte or slag, or matte or copper, and this is the slag layer, which is tapped through this tapping hole at a rather high speed compared to the phase below, and this velocity difference has a drag force here on the interface, and that drag force captures some of the more heavy liquid, along with this faster flowing, this case slag flow. This the same happens in all, whether it is tapping situation or overflow situation. If the layer of the heavier material below is too close to the tapping hole. So this kind of thing is the other possibility. So even if all droplets of matte and metal have been settled, we can spoil the quality of slag by tapping the material with a too high level of the matte below. So it is entrained, and this is entrainment we don't actually see in the polished sections of the slag samples taken from above here, but we see it when we are settling the slag in slag ladles. So it's very important that these tapping situations are carried out carefully, and there are also another mechanism of being entrained for matte or metal into the slag than just pure settling into the like in flash melting furnace. So let's have a look on the converting products then. So we have, as I mentioned in my earlier slides, we have a batch-wise operation. These all sub-steps are taking place in the Pearce-Smith converter. We have several slag blow steps, typically from 2 to 4, in even 5 in industrial smelters, which each of them they are producing slag, then SO2 and silica and coolants are added, and once the charge amount is reduced and some slag has been removed, meaning iron from the mat has been removed, so more mat is added, more reverts are added during blow, and more silica is added for slag making, and these kinds of slag blows, they are producing slag which is except the last one, which is going into slag cleaning operations. And after the last slag blow step has been finalized, so then this copper blow converter is now full of white metal, and the residual sulfur is being oxidized. Metals like spent anodes from refinery are used as coolant. These reverts may be low grade copper scrap or whatever, containing much less than 90% copper. They are at the same time refined there, but coolants in copper blow, they typically are pure anode copper, which is coming back as spent anodes from electrolytic refining step. And because we are not producing slag here anymore, so there must not be any elements which are oxidized in the copper blow stage. And the resulting material is called blister copper. So we have final slag here, which often remains in the converter, waiting for the next furnace mat ladle and charge. And this blister copper, this is poured to anode furnace. So this kind of step-wise approach to anode furnace and blister copper, depending on the size of the converter, produces a few hundreds of tons of blister copper. Oxygen enrichment in P.O. converters in these steps, it's low. It's few percent only, 5 probably, not about 10% anyway. So this is essentially the blowing gas is air with some extra oxygen, increasing certainly the productivity, but higher oxygen concentrations in the blow would damage the converter, and it is not practiced in industry at all. So what kind of material is blister copper? So it is copper which doesn't, crude copper which doesn't anymore contain iron. So even if the white metal, when it is saturated with copper, it may contain 1% or 0.5% iron. So the blister copper generating from that is essentially iron-free. This can be this has been actually shown in experiments as well as in computational way. But what that blister copper, and why it is called blister copper, it is because when its sulfur content, this is equilibrium diagram at several temperatures, with in equilibrium with pure SO2, 1 atmosphere. When we decrease the sulfur content of our blister copper at certain temperature, at the same time we are increasing its oxygen content, and typically we are blowing sulfur to rather low levels in Biosmith operations, and that means that our oxygen already, when dissolved in copper, already when it comes to the anode furnace, is rather high. And now we might ask, what is happening if we start solidifying that kind of copper containing a certain amount or certain fraction of sulfur, and in addition to that, it contains oxygen. So it starts, when it is cooled, it starts generating SO2. Its SO2 solubility is decreasing depending on how much in which part of this curve we are. So it generates more or less SO2, and then starts generating oxides or sulfides in the solidifying copper. And that is not acceptable for two reasons in the electrolytic refining. The first reason is the bubble formation, which are called blisters, and that is distorting the geometry of cast anodes. So they are not geometrically stable. And the other one is that it's not nice to have sulfides or oxides in the anode, because they are not converted into cathode copper. So what we do in anode furnace, we refine this blister copper so that we are essentially removing all sulfur to rather low concentrations, meaning that in the end point of anode furnace oxidation step, removal of sulfur, our oxygen concentration is somewhere around 1% or in that range anyway. So then we have to do something with that oxygen, which is dissolved in the anode, and not yet in anode copper, but this crude copper, and we blow through the 2 years either methane, so natural gas, or in some cases ammonia, which probably is more environmentally friendly reductant. So these are used for eliminating the formation of oxides when anode copper is cast into anodes. And this is the end of the anode kind of stream in the copper smelter. This is called foundry. So it is casting anodes of strict weight and very close dimensions. So it must be straight anode for electrolytic refining, because the spacing of electrodes, so cathode anode spacing, must be uniform in those thousands and thousands of anodes treated there and refined electrolytically. They must be fulfilling rather tight specifications, and they are cast in this kind of casting tables, which are taking a certain amount of copper, cooling it down, and then after cooling they are quenched in water, taken away from that casting table and quenched in water. And this kind of twin wheel cast shop probably is also in case of the new Indonesian copper smelter. So this anode copper contains essentially all gold and silver fed into the smelter. It also contains a lot of selenium, tellurium, and those impurities which have not been oxidized away in the smelting, matte smelting, or in the converting steps. So they are captured into electrolytic refining. They end up in the non-soluble material collected from the cells, electrolysis cells, as a material called anode slime. It is a powderous material containing gold, silver, and platinum group metals, and they are in form of selenides and tellurides, bismuth and arsenic, antimony. They may be as oxides in there, and they all can be recovered to metals if needed. So this is the end point of a smelter and end point of the pyrometallurgical operation of copper smelting. And after this the tank house, as the electrolytic refining is also called, is taking care of the purification to this purity of more than 99.99. Probably there's a 5 after that fourth 9 as well. So it's very pure material, and some of the impurities have also maximum concentrations allowed before it can be sold as standard grade copper cathode. Typically in Europe we call LME grade, A grade copper and cathodes, which have long list of elements, including bismuth, antimony, arsenic, with 1 ppm or 2 ppm of each, which are allowed, and the only element with higher concentrations of ppm or 2 levels is silver, because it doesn't impair doesn't make the conductivity of copper lower. It doesn't harm its physical properties, but mostly all these impurity elements in cathode copper are on the level of 1 ppm, 1 part per million in weight. Now a few words about continuous converting. So as I said, this Peer-Smith converter is batch-wise. Typical sizes are 2 to probably 400 tons of material, and batch-wise operation is not very nice because you will need a lot of skills from shift to another to do the job in the same way, in a consistent way. This is one reason. The other reason is that most SO2 emissions of today, they come from Peer-Smith converters, because these hoods are not fully tight. They always have leakages from natural reasons, and that is why continuous converting operation would lower emissions. It would generate more uniform product for the converting step, and because of this transfer of materials in the smelter by grains, molten material, fuming material, ladle transport, that would be removed from the smelter operation. So these all, so better hygiene, better environmental performance, better quality of the product. These are things which are favoring continuous converting technologies. We have today 2 industrially used continuous converting technologies, and bit slightly older is the Mitsubishi technology, which is used in Indonesia today, and it is based on an idea that we can move materials in covered launders, ventilated launders, from one furnace to another furnace, which is a bit lower in its location, and further on into 3rd and 4th furnaces without any cranes, without any ladle transport. And this Mitsubishi technology was developed in early 80s, and it is based on bath smelting process in the smelting step and in the converting step. So this is one technological kind of solution, and it is used in less than 10 smelters in the world today. And from thermodynamic point of view, the converting step is rather unique. In Mitsubishi furnace converter, there is on top, there is a mat in the middle, and on the bottom of the furnace there's a copper, crude copper, and after that certainly anode furnace fire refining is needed for the same reasons as after Peer-Smith converting. But now this three-phase, three-layer operation means that the sulfur concentration of forming blister copper depends on temperature. It cannot be selected, and it depends on the phase diagram I showed you earlier. It depends on the behavior of this phase boundary, because we have always white metal and copper there, so the copper contains always a fixed fraction of sulfur depending on temperature. It cannot be lower because otherwise we don't have any mat around. So this means that Mitsubishi technology needs a different type of fire refining step, which is capable of removing much higher sulfur concentrations from the blister copper than Peer-Smith converting. So this is one option, and this is very good in terms of environmental aspects and on-site hygienic performance. I have been in Timmins in this kind of smelter in Canada, and it was very clean, extremely clean place, and without any fumes or SO2 leakages. So this is one option. What is nowadays more preferred, for one reason or another, I don't know, is the technology called flash converting. So we have in flash converting, we are using solidified and ground flash furnace mat, which is cold material, can be stored at site in big heaps, and when that is ground to suitable fineness and fed in flash melting furnace with pure oxygen, so it can be oxidized directly to blister copper and slag. And there is no, these flash converting furnaces are then much smaller than flash melting furnaces, and these flash converting furnaces don't have three layers they don't have mat layer in between slag and blister copper. They are operating in two-layer mode, and that is why the sulfur content of that forming blister copper can be anything. It can be saturated with with matte, but it can be, which is more than 1%, but it can be oxidized down to 0.2 weight percent. So then we don't need any specific fine refining technology for treating that material anymore. So this is one advantage. So new inventions, new skills are needed in operating flash converting if the smelter stuff is used to do that in biosmith converting. But it is continuous process, feeding continuously ground solidified matte, and it is tapped in a similar way as tapping in flash melting is carried out. So both Mitsubishi technology and flash converting technology is using lime fluxing. So it's not added typically as lime, it's added as limestone. So because of its capabilities, which I tell you a bit later. So it's more expensive, but slag amount is small, and it's affordable for that reason. So we have nowadays 5 big units of flash smelting, flash converting smelters in the world. First one in USA, Kennecott smelter in Utah, and 4 more in China, and the big one to be built in Indonesia is the 6th unit. They are all large smelters, 400,000 tons of copper per year, and this Indonesian unit will be 500,000 tons of copper. So it's very, very effective and producing uniform blister for anode casting and fire refining and casting processes, and further on to electrolytic refining. Also, its sulfur capture or degree of sulfurization is very high. It's on a similar level as in flash melting, even higher, because as you see later, there is rather high because the gas is technical oxygen, so the concentration of the off gas is very, very high. It's 80%, it's 90% or something. So the operation of sulfuric acid plant is highly effective as a result of that. So what happens in the flash converting furnace? So we have a similar type of concentrate burner, which is distributing the solids, mixing the gas with solids, and making the suspension here, and it is ignited by itself by the heavy radiation and hot gases of the reaction shaft. So we burn all sulfur from the matte. We burn all iron from the matte and generate SO2 and then iron oxides. And this is fundamentally the same chemistry, but from rather different type of raw material, because to keep the amount of slag in flash converting on a low level, the material fed into the reaction shaft contains about 70% copper, so it's matte grade of the flash furnace matte is about 70%, and that is, from one hand, it is enough sulfur and iron to make that combustion taking place here in the suspension, to make it homogeneous. No extra energy, no extra fuel, no oil is needed to keep this oxidation step running and generating all heat from the whole furnace, compensating the heat and so on. And then on the other hand, as I said, to keep the slag formed in flash converting, to keep its amount low. And why that is important? It is important because the concept keeps the idea in it that flash converting, flash smelting smelter generates only one discard slag. So the slag made in here in the flash converting step is fed back as such without any treatment to the flash melting step. So there is a certain lime addition to flash melting from flash converting step, and that internal circulation has been meant to be as small as possible in order to allow as effective operation for the flash melting step as possible. So that there is no too much extra cold material fed into the flash melting step, which is the case if we lower this copper grade, we increase the amount, the volume of slag formed in flash converting, and then that material of the granulation, when it's fed back into the flash smelting step, that needs energy, which mostly is how to say, it's useless. It's not supporting the production. So what kind of slag is calcium ferrite slag? What kind of slag is formed if we flux iron oxides with lime? And it's important to know how copper is dissolved in this slag, because that is actually the driver, the carrot, why we are using lime fluxing. And lime fluxing comes from the fact that it, at the same oxygen partial pressure, at the same temperature, it dissolves less copper chemically, and this is one important feature of calcium ferrite slags. here you see an isothermal section of calcium oxide FeO Fe2O3 system, pure calcium ferrite slag system, and the actual slag molten slag phase is here. This area called oxide liquid. It is the slag phase, and these red lines are again oxygen isoactivity curves, oxygen isobars, iso partial pressure lines of oxygen, and you can see these are in atmospheres. So you can see that, and this diagram has been plotted and calculated at 1250 C. So you can see that this molten slag phase is stable up to pure oxygen. It is more stable slag in terms of oxygen pressure than iron silicate slags, and this is a very good feature, and this is something which is even important in converting conditions where we are at low sulfur contents in blister. We are around 10 to minus 4.5 or minus 4, between that range of oxygen partial pressures. So it would be rather tricky to run a smelter where your slag is not one phase but contains solid phases which form because of these thermodynamic boundary conditions. But calcium ferrite slag is stable up to pure oxygen, and from ion saturation up to pure oxygen. That is a very significant issue here. They are dissolving slightly less copper in it in similar conditions compared to iron silicate slags, and that together with this higher stability, more wide range of the molten slag in terms of oxygen pressure, they are important features, and that is why calcium silicate or calcium ferrite slags are used in all continuous copper converting facilities. As mentioned in my headlines, I will talk also very shortly about one-step copper smelting. One-step copper smelting is a rarity. You can produce copper in one step only from very small number of ores and concentrates. And we have such rare examples in various parts of the world where we have either very high copper concentration in the ore or very low iron concentration in the ore. So in such cases, when we have little iron compared to amount of copper, we can produce copper also in one step without converting, without smelting in between. And this is because such concentrates which have a low iron to copper ratio, they produce much less slag in smelting. So whatever the solubility of copper in the slag is, so at some point when this iron to copper ratio is going down, at some point the treatment of slag cleaning is not an issue anymore, technologically, nor financially, nor in terms of recoveries. And this feature allows us to at least on kind of as an exercise on table on tutorials, we can imagine that we can do copper smelting in one step. Actually, there are 3 such furnaces built in the world since second half of 1970s. First direct to blister smelter was erected in Poland. Was started up in 1978, and since that 2 more have been built. One in Western Australia, northwestern Australia anyway, and that the other one in Zambia, Zambian copper belt area in northern Zambia. So they are much simpler in terms of the flow sheet. So there is only concentrate preparation, smelting, gas drain for off-gas treatment. But blister is then fed into anode furnaces for fire refining and anode casting, and slag is treated in slag cleaning steps. How many they are, it depends on the raw material. And slag cleaning is also producing blister copper. Some different type of blister, but anyway. So this is very, very simple flow sheet. It doesn't need any cranes or ladle transport materials either. So the smelter building doesn't need to be so high, and it's cheaper to erect, cheaper investment, and there are no problems with the logistics, crane movements, and so on at the site. So there are lots of kind of positive features in direct to blister smelting, but actual, if there is any problem, but the weakness of this is that normal chalcopyrite type concentrates cannot be smelted in here economically. They are not viable. So all these 3 direct to blister smelters are flat smelters, and in the reaction shaft the oxygen coefficient, which I explained on Monday, oxygen volume per ton of feed material, feed mixture, is much larger than in matte smelting, because we are now oxidizing all iron, all sulfur, and everything is taking place in this reaction shaft. So during that so-called free fall of the particles, feed material particles, together with the process gas, which is heavily enriched air, oxygen enriched air. So this means that all gangue minerals present in the feed mixture, they are present in the direct to blister slag. So this may be a problem, this may be a challenge at least, and it is a challenge. And this also means that as we are producing metal copper with only some sulfur in it, so that means that our slag chemistry, it must be so that it dissolves all these gangue minerals, and the slag is stable. It is kind of modified in such a way that it is stable at high oxygen partial pressures. So this is much more tricky fluxing situation than continuous converting, for this very reason that all the kind of goodies coming through the feed mixture, they depot in the slag. And this is because all those furnaces are delivered and designed by current Outotec or Metso Outotec. So we have been analyzing what kind of slags could be used and will be used in these smelters, and it appears that these direct to blister smelters, depending on the feed material, they can be run on calcium ferrite chemistry, but they actually can be run also with iron silicate chemistry if the kind of gangue material, gangue minerals are suitable. And then probably we can also use something which is called calcium iron silicates, those intermediates of iron silicate and calcium ferrite, which are not used in any smelter yet, but probably it may be possible. So in these iron silicate chemistry cases, we have somewhat higher copper concentration in the slag, but it has appeared that this cleaning step in electric furnaces is rather robust and flexible and fast, and it doesn't very much kind of limit the productivity. So this is example from that Polish smelter, which is using modified iron silicate slags, and their how to say, operational point is in 0.3 weight percent sulfur in the blister, and in various feed mixture options that iron silicate chemistry, which has rather much alumina in it. It is producing slags with about 20% copper in it, and in KCM smelter in Zambia, probably we are at around 15% copper in the slag at the same sulfur level in the blister. So here is an other example. This is kind of desktop study only, but showing you which type of how to say, material streams we may have in a direct to blister flow sheet. This is furnace, this is slag cleaning, and it has also after electric furnace slag cleaning, it has a milling and flotation step for getting out of the residual copper, which is not very well removed in electric furnace. It's still on a rather high level here, but after slag concentrator, the discard slag contains about 0.3 copper. So we have one point is here we have slag containing 20% copper going to electric furnace. We have off gas containing more than 50% SO2 going to the acid plant, and then only 1.6 tons of slag concentrate coming back from the concentrator to the smelting step, where the feed is almost 100 tons. So this circulating load within the smelter is not due to dissolved copper is not substantial. Dust is much more. It's more than fivefold in compared to that. I think this is my last slide on copper. So
okay, Pekka.
I think we have now plenty of time for
yes,
discussion, questions, and comments, whatever you
okay, Pekka. Because normally, like yesterday, we are running out of time. Still get a lot of questions. Okay, guys, thank you. Please ask question. Don't be shy. Okay, I see some face here of my student. Okay, first questions.
Hello, Sima. How to ask question?
Okay, Abrar. Okay, yeah, I can. Yeah, if you saw your video, if you say something, so I will directly know you. Okay, but if you turn off your video, I don't know who you are. So Abrar from Indonesia, I think. Yes.
Please.
Of course, because you are my student. Yes. Ask.
Go ahead.
Yeah. Hello, Pekka. My name is Abrar Temula from Institut Teknologi Bandung. And I want to ask you about pre-Smith converting. In the PS converting, there are two steps of slag blow. My question is it possible to do it in just one step with adding more quantity of mate, silica flux, or another component in just one step of slag blow?
Yes, it's possible, but it's not practical. Because because the volume of the batch of the charge, it decreases so much that and you can't fill the converter with large amount of material. Its volume is limited. So the reason why you are doing several, typically more than 2 slag blows, 3 or 4, is that the batch gets smaller when it is losing iron, losing sulfur, and when that slag is removed, more matte from the smelting furnace is added, so more copper is added into the converter, and then the next blowing step is accomplished, and again slag removed, taken away, and new matte is added. So it is a question of practicality. If you can do it in large volume, it's more effective, and it also, I would guess, I can roughly estimate in my head that if you would do it in very small converters, in one slag blow only, you would have much bigger copper losses into slag, because in multiple blows you are not blowing each charge iron free. You leave some iron and in there, and you blow it into white metal in the last slag blow only. And there, when you are in completely iron-free white metal, your losses to the copper losses to the slag are the biggest. They are 3 times, 4 times as big as in case you have 2 or 3% iron there compared to 0. So it's also ineffective in terms of the losses. Yeah, it can be done, but it's not worth doing it.
Okay, any more questions?
Good afternoon, Mr. Pekka. Good afternoon, Mr. Imam. I'm Imelda from Indonesia. I would like.
Okay, Imelda. Yes, please.
I'm wondering if our concentrate has molybdenum. In which part of the process is the smelter collecting the molybdenum, or in which part we can collect the molybdenum? Just wondering if our concentrate has a molybdenum. Thank you.
Okay, the question is if there is any molybdenum in the concentrate, maybe in Indonesia or in I don't know, in Finland concentrate. If there is molybdenum, to which phase molybdenum will go, and in which, maybe in the which process, maybe in the very I don't know what is in term in English. It is in the not in the early process, but in the end of the process of the copper processing, maybe like even processing the anode slime. But I don't know, Becca. You know.
Yeah, I have at least some knowledge about that issue. Molybdenum is present in certain porphyric ores of copper, and it is common kind of, it's a sulfide there. It is common minority metal in South America, Chilean, probably Bolivian, Peruvian concentrates. And what it does in when it is in case it is fed as such into flash melting or smelting or any other primary smelting, copper smelting process, so it vaporizes there because it is molybdenum oxides are gaseous. Some oxides, it is molybdenum trioxide or something. It is gaseous, so it is deporting in the smelting step into flue dust. And if you want to recover molybdenum, you must treat your flue dust separately. In Chile, they are actually roasting beforehand. When they have large amounts of molybdenum in the concentrate, they are roasting it beforehand with very little oxygen, with almost reducing conditions, so that the molybdenum is, because it's very reactive metal, it is oxidized and vaporized. And Chile is very big producer of molybdenum because of this technology. So they have roasters which are pre-treating copper, and that then after this pre-treatment, the concentrate, which is still sulfidic concentrate, it is fed into flash melting or teniente reactor or whatever they have there. They have even one reverb in Chile.
Nice information.
So that is something which in case it is a low concentration of molybdenum, so you probably need to consider its recovery from the flue dust.
Okay, Pekka, I think, yeah, very clear, and it is new knowledge for me also. So if the concentrates contain molybdenum, for example, it is low and it is not pre-treated, so the molybdenum, because it is easy to oxidize and become a gas, so it will go to the flue dust in the smelting process. So in case of higher molybdenum content in the concentrate, like in Chile, there's or in China, there is pre-treatment of the concentrate, and then the molybdenum will be oxidized and become gas. Okay, very nice. Yes.
There is another trace metal which behaves exactly like that, and the Polish copper company started to recover rhenium. Its chemical sign is Re, from their acid plant washing section. Less than 10 years ago, they realized that their concentrates, which are Polish concentrates, they are containing rhenium, and it is vapor. It's oxide vapor. It's going through whole smelter gas train. It goes through the ESP, electrostatic precipitator, but it is washed from the gas in the acid plant. And it's very expensive metal. They started producing it probably 5 to 8 years ago. And they are Polish copper companies now probably the second biggest producer of rhenium. It is used in special alloys for gas turbines and engines, airplane engines, and so on. So there are other elements which may be collected from the fumes and even from the liquids of the acid plant washing section.
Okay, Pekka. More question, guys.
Thank you for the answer. So it is when maybe one more question continue, Mr. Imam.
Okay. Yes, it's okay.
So after
It's nice to
the
have this kind of discussion, you know? Yes.
so after the trace element was or molybdenum is collected on the flue gas, it is directly going to acid plant, right? So mostly
Well,
these elements will
yeah.
be leach on this acid leaching, so something like that. Is it possible to do directly leaching on the acid plant for all the tracing or the, let's say, important elements in the acid plant? So thank you.
There is, before you make the sulfuric acid, so before this conversion from SO2 to SO3 and further on to sulfuric acid, before that is possible, so the gas coming from the smelter must be purified very well. It's not allowed to contain any kind of dust or fumes.
Pekka,
Sorry?
can you hear the Pekka voice, guys?
Yes.
Is there something problem with my voice? Can you hear me?
Can hear.
I can hear it.
Can you hear me? Can you hear me?
I can hear.
Oh yeah, sorry. Yes, my connection. Sorry. I'm sorry, Pekka. My bad. Yes.
Come back, Imam. We don't want to lose you. Okay, well, yes. So the gas going into the acid plant, it must be very, very pure. It doesn't. It's not allowed to contain any kinds of dusts or fumes. So there is a special kind of department before the acid making at the acid plant. It is called washing section, and this washing section it is removing all the solid materials, all the fumes, all the dust, but also all SO3 coming from the smelter, which may be sometimes a problem of the smelter problem. But this washing section is the department of acid making where all these kind of all these rare elements which are deported from the smelter can be recovered. And to my understanding, the Polish copper company is actually recovering their rhenium from this washing liquid. It is called black acid or wheat acid. And that is often used in concentrators as pH adjusting liquid, because it contains also arsenic and probably cadmium and mercury, and that depending on what is in the feed mixture, what is in the ore of the mine. But really that is the place where these last traces of metals which come from the smelter can be recovered and are recovered. And then this flue dust, which is often circulating within the smelter, which is much larger amount of material. If you treat that separately, so molybdenum is mostly there. It's not going into the acid plant at all.
Yes.
It's mostly, I think it is in the normal flue dust, which is coming from the waste heat boiler and
Yes.
electrostatic precipitator.
Okay, Pekka, I think it is very clear. So the gas which containing fume of molybdenum oxide and rhenium, for example, it will go to the acid plant. In the acid plant, before going to the contact process, there is washing sections. So this washing section will take the dust that containing the molybdenum, and we will get a liquor, something like that, Becca, right? Like you say. Yes. So in there, we recover the evaporated trace element in the smelting process. Very good questions. Okay, guys, any more questions? We still have 10 minutes.
Mas,
Actually, we should end 10 minutes ago, but because still we get a lot of questions and nice discussion. Any more questions?
Mas,
Yes, who is it?
Christopher.
Oh, Christopher. Yes, yes, sorry. Yes, Christopher.
Okay, I'm Christopher from Indonesia. Hi, Pekka. I want to ask you a question. What do you think is the main factor that affects the feasibility of copper smelter? Because in Indonesia, copper mining tend to not building copper smelter, or they tend to be reluctant to do that.
Okay. So maybe the question is, you know, Becca, it's long history before Autotech that want to build. It is our government. It is also the reason why I'm going to Finland. It is the rule, the policy about the concentrate ban of copper is implemented in around 2010, but it is more than 10 years, you know. So it is like our government try to encourage the copper mining company not to just export, please build the copper byte, but they are reluctant. It is take long time for them to build, and I think that's the question. Why they reluctant? Why they don't want to build? Is it not so I don't know. Maybe the income is so small. I don't know. Too risky.
I don't have any clear answer to that question, but I have been following this mining business now for more than 30 years, not being a mining engineer myself, but I have some friends and colleagues in big mining companies outside Finland, certainly, because we don't have any big mining company here. But it seems to me that, well, the business of exploration and mining is as a business, it is rather far from smelting and making metals. So even if these mining companies, big ones, Rio and BHB and whatever they are, Freeport, they are very good in exploration. They are very good in mining and beneficiation operations. They seem to be not willing to own smelters. Many mining companies used to own smelters in the past, but they have been selling them out and not running them, only probably owning smelters, very small shares of them, not half, not probably 1/4. So the mining business seems to be concentrating very much on mining only. And then we have smelter companies which are doing the smelting and probably also selling the metals, which is again different type of business than selling concentrates. So different customers, different kind of arguments and different types of money flows and different responsibilities. So yeah, I think that mining companies are looking at smelting business as something they don't need to do, even if it is increasing the value of the concentrate or ore. But the value increase is probably coming too slowly. It's needing too much investments, too much capital, and because mining is it is concentrate. Mining is in hands of big companies, because mining business is needing huge amount of money before the gas flow is coming back to the mining company. So it's a different type of business from smelting, and I think that is why they don't want to be involved in smelting and refining business. This is clearly seen in copper and zinc, probably in lead as well, and I don't know, nickel, it is not so clear, but it must be so in iron ore as well. So it's mining companies are so focused on mining, and it's a business where you need a lot of money. I don't know how much this investment of Indonesian new smelter, how big it is in US dollars, but it must be 1 billion or something. And if you establish a new mine, big mine, anywhere in the world, it is many times of that. I was in Mongolia some 9-8 years ago, and when they just started the kind of erecting the mine, very big copper mine in southern Mongolia, Oyu Tolgoi mine, which is probably among the 10 biggest copper mines in the world. And my feeling was that the investment cost of that mine alone, that was around $5 billion US dollars, 5,000 million US dollars. And the national budget of Mongolia was probably from 10 to 15 billion. So it was one third of national budget of the country. It wasn't invested by one mining company. It's a group of companies. I think Rio Tinto is one of them. I don't remember who are the others. But really, mining business is a business of its own, and probably these special features are how to say, if you have mine and smelter, and you invest your money in those two operations, it's a huge money, and you can, if you sell your concentrate,
and you will get copper price directly
to other companies in the world, you get much sooner your money back than if it is processed first in your smelter and then sold as ready-made
yes.
cathode. Yeah, that is a very complicated thing. It may be, you maybe need to read couple of business economics books, textbooks from that very area to understand that, but it's not simple question at all.
Yes. Yeah. Okay, Chris, well, it's not simple question, but I think from PK answer, one of the reason is like the peg bed period. It is need longer time, maybe 20 years. If you build copper smelters, I also have ever read that kind of PK explanation. It is maybe take 20 years in order you get your money back. It take longer time.
Yeah.
But if you have money and you invest in mining and producing concentrate, it's quicker. Okay. So if it is quicker, the risk is also smaller, I think, because of time. Okay, Becca. I think it's already 4, Becca. Thank you very much.
Thank
I
you.
see today more than 100 students coming, but now